All right, so in this video, I'm going to go over the solutions to the review section for gas laws, all right, which also goes by the term movement. All right, first of all, whenever you're doing gas law problems, remember that you often have to convert your temperatures from Celsius into Kelvin, or you might have to convert it back the other way. All right, and the formula for how to do that is that Kelvin equals Celsius plus 273. I just want to remind people that that formula is in the formulas guide. If you take a look at the formulas guide on your sheet, you can see it's right there. So it's not even something that you need to memorize. So that's how you would do that. All right, converting 735 millimeters of mercury to kilopascals. One thing that is very helpful in that is in looking at the formulas guide. When you look at all the conversions of what is considered, or all the values of what is considered standard pressure, you'll see all of these values here for standard pressure. All right, and you can see kilopascal and millimeters of mercury, so you can see the relationship there. All right. So we can see that 760 millimeters of mercury is going to be the same as 101.3 kilopascals. And you can just set up a one-step crossbar. All right, so this is a true relationship, all right, where these things are equivalent to each other. So you could just set them up so that the units are diagonal from each other. And you would just multiply these two numbers and then divide them by 760. All right, in the next problem, we have a gas is at a volume of 4 liters and is allowed to expand to a volume of 8 liters. What happens to the pressure in the container if the temperature remains constant? All right, so in this problem, it's essentially, think about it this way. If we take a syringe, all right, just take a normal syringe and you compress it, all right, syringe is the thing that you get a shot with, all right. When you reduce that volume, all right, you're forcing the air to be in a smaller amount of space, and the pressure inside of there goes up. All right, if you've ever used a tire pump, you know that like as the tire starts to get filled, when you push down on the plunger, it gets hard to push down. All right, so as when you have the lower volume, you're going to have the higher pressure. All right, so think about this as if you were turning this into reverse. All right, if you had something that was at higher pressure and you allowed the volume to get bigger, you would then have the pressure would be lower in the end. All right, so just to answer this question, just think about this process in reverse, and you can answer it that way. So if you wanted to, though, one thing that you could do is just in your mind make up an imaginary starting pressure, and then you could use P1 V1 equals P2 V2 and just calculate what the resulting pressure would be. That would also be a way of telling you what the answer would be. In the next problem, what would the volume of 2.5 moles of oxygen be at this temperature and this pressure? All right. So this is a case where, notice, there is no change going on. So there's no ones or twos in this problem. This is an ideal gas law problem. PV equals nRT. All right, it's asking for what the volume would be. So the volume is going to equal nRT over P, so that you're just rearranging this equation right here. And then you're plugging in your values. All right. Notice that in this problem, it gives the pressure in atmospheres. So make sure that you choose the example of R that involves that particular unit. All right, so this one's got atmospheres right here, so that's why I'm choosing that particular value for R in this equation. All right. In the next problem, calculate the number of liters occupied at STP. All right, anytime you see STP, automatically write down that the temperature is 273 Kelvin, and your pressure could be a couple of different things. In this one, it doesn't matter which one we use because it doesn't specify calculate it in, atmospheres or millimeters of mercury. So you have a choice, all right? So you could have chosen this one, or this one. If it gives you, remember, if you have an ideal gas law problem and it gives you pressure in a certain unit, you'll have to pick out the one that matches, like we did in the previous problem. But on this one, notice that they don't ask you specify which one you use. So I'm just going to use atmospheres, all right? Because standard pressure is 1.00 atmospheres. It's a nice, clean number. So because I'm using atmosphere here, notice I'm using this value of R when I plug it in, all right? And when you solve for this, you will get the answer for that. All right, in this problem right here, if the temperature of the balloon with a volume of 45 is raised from 22 Celsius to 58, what's the new volume? All right, notice it does not mention anything about pressure changing. All right, so we're going to assume that pressure is constant. This is a case where you do have change. So you're going to have those ones and twos in the formula. All right, so how do you figure out the correct formula? Whenever you've got some sort of change going on, remember that the base formula that you can always use to figure out your formula is this one right here. All right, P1 V1 over T1 equals P2 V2 over T2. This one is called the combined gas law, and recall that the reason that is useful is that when once you write it down, once you determine that one of the things in this does not change, for example, in this problem right here, notice pressure does not change. All right, so therefore I can essentially cover up the pressure part of this equation. And notice if I just cover up the P's on both the left and the right side, it becomes this equation right here. All right, and that's going to be the equation that you can use to solve for this problem. It's asking for what the new problem volume would be, so just solve for your V2, which is going to be that. Go ahead and plug in your numbers, and it gives you 50 milliliters. Notice that in this problem, I put the period at the end of that just to indicate that this number would have two significant figures. This is one of these situations where the number that comes out of your calculator, when you round it to 2 sig figs, ends up being 50, all right? And if you just looked at 50 by itself, you would assume that it's just one significant figure, so you want to include that to indicate that that is actually has two significant figures. The next problem is just another standard ideal gas law problem. In this problem, it's asking you to calculate the pressure. Notice that there's no language in this that involves something changing, so that's kind of a giveaway that it's using this equation right here. Solving for pressure would give this, and then plugging in for the rest of the values. Notice that in this problem, it doesn't tell you what units it wants the pressure in. So make sure that when you do what that means is that you're allowed to use any of the values of R that you wanted to. All right, I just happen to choose this value of R, but notice in order to answer the question, just make sure that you put in the units for R. All right. In the next one, what is the mass of 24 liters of carbon tetrahydride at standard temperature and pressure? All right, again, those would mean these values right here. This is going to be our volume, so we could rearrange this to calculate the number of moles. All right, calculating that, we would have 1.07 moles of that, this chemical right here. And we can turn moles of that into grams of that through a one-step crossbar. All right, and again, the way that you get this number right here is just to calculate the molar mass of CH4. Okay. In the next problem, you could have actually calculated it one of two ways. All right, when I'm going through this, this right here, I would say that's my initial temperature. All right, here's my initial volume. Here's my initial pressure. Here is another temperature reading, and it's saying what would the new pressure be if this was the new volume. All right, so when I'm looking at all the variables in that, it looks like we have P1, B1, T1, and we also have P2, B2, and T2. All right. If you're really paying attention here, though, there's something that you can do to make this easier. Notice that the temperature, the starting and the ending temperature, are the exact same thing. All right. So what that means is that the temperature is constant. All right. And if the temperature is constant, meaning it doesn't change, this equation would become the same thing as this right here. All right. So if you wanted to go ahead and just completely ignore the 340 Kelvin temperatures here and just focus on plugging the remaining values into this equation, it would work. All right. If you wanted to go ahead and do this, all right, you can still do it that way. Notice that it asked me to calculate the final pressure, and so I solved for P2 here, which is going to be this value right here. And when I do that, notice that when I put in the 340 Kelvin for both the T2 and the T1, you end up with the same value in the numerator and the denominator, and they would just cancel out. All right. And so that's why, essentially, mathematically, why you can go ahead and cancel them out if they don't change. All right. Because if you left them in this equation right here, they would end up just being numbers where one would be in the numerator, one's in the denominator, and they would just cancel out. All right. So either way you wanted to do that would be fine. And the next section is, has much to do with just states of matter. All right, just identifying states of matter by their properties. Notice that in these, I've gone ahead and taken out the mention about kinetic energy. That can be a little bit misleading here, so I don't want to focus on that right here. You can identify these by all the other information, though. All right, if something where the particles can disperse freely, all right, and separate from each other, that's going to be a gas. All right. There's one state of matter that we really have not talked about in this class. It's actually a very common state of matter in the universe, but there's very little of it here on Earth. That is plasma. All right. It's essentially kind of like a gas, but the particles are charged. Only place you'd ever see this on Earth is like in the middle of a lightning strike. But in stars it is very common. All right, where you've got a fixed volume and very orderly particles, and the particles are touching each other, that's a solid. And where the particles can move past each other, that's a liquid. All right, and the last little bit here, these forces. All right, attraction between two polar molecules, that's dipole-dipole. London dispersion forces, remember that's the attractive forces that can occur between any types of material, and it occurs because you get this situation where electrons are moving around randomly in bonds, and that creates what are called temporary dipoles, which create little areas of stickiness between neighboring bonds. All right. Again, when you have these attraction between the instantaneous dipoles, or I actually refer to those as temporary dipoles, that's going to be the London dispersion forces. And then there's this special type of dipole-dipole interaction, which involves molecules that contain hydrogens connected to either nitrogen, oxygen, or fluorine. All right, and that's hydrogen bonding. All right. Again, I recommend going back to my notes on this particular topic. I go into it in more detail there. But these would be the key elements of that. All right, the last four right here is just going to be to note what would the major attractive force be in these types of materials. Carbon tetrahydride, there are no polar bonds. All right, to have dipole-dipole interactions, you have to have a polar molecule, which means you have to have a polar bond somewhere, and this does not have any polar bonds. All right. Notice I changed this. Sulfur difluoride, if you did that molecule, it's going to be a bent triatomic molecule. This is going to be a polar bond. So you're going to have a polar side, a delta positive and a delta negative side of this molecule. So this is going to be dipole-dipole. Elemental fluorine, there are no polar bonds. London dispersion force would be the only force that's significant there. And then nitrogen trihydride, that is going to be it's got a nitrogen-hydrogen bond, so that should be your hint that that's hydrogen bonding.